Great.
Yeah,
Okay, so our next speaker is Sophie Hosseini from Durham, and she will talk about higher form symmetries, or higher symmetries, sorry, from geometric engineering. Please, Sophie.
Hi, I would like to first thank the speakers for inviting me to give this talk. I will talk about my work on geometric origin of higher form symmetries. This is work based on the papers here done in collaboration with my advisor Iñaki and collaborators Federico and Miguel. Okay, so it was originally thought that a quantum field theory is fully specified by its local operators and their correlation functions. But we know that the higher dimensional operators are also important and they can have higher form symmetries. In fact, there are quantum field theories which have the same local structure but different global structures. And having different choices of global structures means that it affects the phase structure of the theory and can have important consequences. For example, difference with theories with different global structures have different partition functions. Now, high form symmetries are especially useful in the study of quantum field theories for which we don't know a Lagrangian, as without a Lagrangian, we otherwise have limited tools to understand them. They are also useful to study dual theories, for example, in the sense of electromagnetic dual theories, or we could use them to see which theories are dual each other in the sense of RG flows, because we expect them, if they are dual, we expect them to have the same higher form symmetries. There are various applications, like we could study confinement using one form symmetries, or we could study their anomalies. Some extensions include, so we could go on and see if we can combine these higher form symmetries to see if they form higher group structures and more interesting categorical symmetries. Okay, so the goal of this talk is to discuss, first of all, what are higher form symmetries, and then I would like to go further and tell you how this can be obtained in a systematic way from string theory. I will do this by giving some examples. So yeah, here I say that we can use this result to understand how theories with the same local structure have different global structure. Okay, so I will quickly tell you give you the definition of higher form symmetry, and then I will get into to see how we can obtain them from a string theory. Okay, so we say that an n-dimensional quantum field theory has a key form symmetry with group G if there are charge operators UG such that they satisfy certain conditions. So these operators UG, they are labeled by elements G of the symmetry group, and they live on codimension Q+1 manifolds. So they must satisfy the following conditions. These operators must be topological as long as they don't cross any charge operators. So say we have this operator UG of sigma, and then we deform it to say U prime of UG prime of sigma, then as long as we don't cross any charged operators, then UG of sigma is same as UG of sigma prime. Furthermore, they act on charged operators, which we call O, and they live on the Q-dimensional manifolds, which link sigma. So to see what I mean, let's look at an example. So in 3-dimensional quantum field theory, say we have a charge operator UG living on a 1-dimensional manifold acting on O, a line operator, charged operator. Then we can represent this schematically with this diagram. So this is our operator UG of S1, and it can be linked to this operator OS such that we cannot separate these without one crossing the other. And if we do cross it, what we get is a phase like this, and then our operator charge line operator plus our charge operators. So there is, sorry, just to be clear, there's these UG are charge operators, and these OL which they act on are charged operators. So then now that we have separated these, then we can shrink this to 0 to a point, and then it's trivial basically. So what we are left with is a phase times our line operator. Okay. Finally, they need to satisfy the group multiplication law given here. So two operators multiplied by each other is with the label G and G prime in our symmetry group must equal to U of G, G prime on the same space. Okay, so now we can see that this actually gives us, as we expect, the definition of ordinary global symmetry that we are familiar with. So these ordinary global symmetries are zero form symmetries because we have zero-dimensional charged operators, which we know as local operators. And so in 4 dimensions, the charge operators would be 3-dimensional surfaces linking the lines. Okay, now let's look at an example where we have one form symmetry. So that is here 4D super Yang mills with Lie algebra SU2. So we are interested in one form symmetry, so we should have line operators, and then the charge operators here would be 3-dimensional, and so in order to link with them. And so the question is, what are the line operators in 4D super Yang mills? And the answer is that this depends on the choice of gauge group and additional data. So for example, if you pick the gauge group to be SU2, then our charged operators would be Wilson lines that are electrically charged, so we get an electric one-form symmetry. And if we pick the gauge group to be SO3, then we have 2 options. We could have magnetically charged lines, which are tooth lines, or dionic lines, in each case we get magnetic or dionic one-form symmetries respectively. So this is beautifully explained in this paper by Aranis, Laberg, and Tachikova. And we can follow similar analysis for other theories which have a Lagrangian and a gauge group. But what about the theories that we don't know a Lagrangian for? How do we proceed? So one way to do this is to try to construct quantum field theories from string theory and see and try to obtain their higher form symmetries. Okay, so say we start with a string M or F theory in 10, 11, or 12 dimensions respectively, and then we reduce it on an internal manifold X to get a field theory on a lower dimensional manifold M. Then, okay, so this way I'll explain to you how we can obtain the higher form symmetries. But before I do that, let me specialize the case of type 2B in 10 dimensions to make it easier to follow the construction. So in this case, I reduce type 2B on a 6-dimensional internal manifold, and we get a 4-dimensional theory. Okay, so in field theory, the space of field configurations is given by a Hilbert space. Say we have field theory in 4 dimensions, then we construct this Hilbert space by quantizing the theory on R3 cross R to get a Hilbert space on the 3-dimensional in 3 dimensions. So in a string theory, we would like to do something similar. Now, going back to our example, if we start with 10-dimensional type 2B and get a 4-dimensional theory, then we are, in order to get, say, for the Yang-Mills theory, we want to our 6-dimensional internal space to be a cone over a 5-dimensional surface, say Y5, with a singularity, isolated singularity. So if we take the time to be the radial direction, then this we say that this Y5 is the boundary, this whole thing is X6. So this Y5, it would be the boundary of X6 at asymptotic infinity. So Now, before we go on to get a Hilbert space, let us modify the geometry so that, okay, so I forgot to say, so this is the x6 part. We also need to multiply this by M4 to get our 10-dimensional manifold. And then we want to modify this geometry, as I was saying, so that every special slice has the form of the boundary of x6. So this is like, should be dashed kind of, times the M4 manifold, supposed to be the same thing, we're not modifying that. And then once we do this, we can quantize our theory on M9 times R, similarly to field theory. But we would like to take M9 to be the boundary of our 10-dimensional space. So because here we are interested in theories, 4-dimensional theories which are compact, then we can write the boundary M10 as M4 times the boundary of X6. So we want to take M9 to be this boundary of our 10-dimensional manifold, and then we get a Hilbert space on the boundary. Okay, now why are we interested in this non-compact manifold M10 is because because that's what we need in order to get a higher form symmetries, as I will explain. But the interesting thing about non-compact manifolds is that they have, so say this is a non-compact manifold like this, with this boundary, then we could have here cycles which wrap the bulk like this, and these would be compact cycles, elements of, say, the first homology of M. But here we could also have cycles which extend to infinity and are non-compact. So say we have this kind of cycle, and so if we identify all the points on the boundary, these points would identify, and we get a cycle which is element of H1 of M relative to its boundary. And this is a non-compact cycle. So non-compact cycles are interesting because when DP branes, they wrap non-compact K cycles, they result in P minus K plus 1-dimensional charge operators, which are known as surface defects. And these surface defects, they can be screened by dynamical operators, which themselves arise from branes wrapping compact cycles. So now the subset of these defects, which are not screened by the dynamical objects, they can result in discrete P minus K plus 1 form global symmetry because they can be charged under them. So we define the defect group to be precisely the subset of these defects which are not screened by the dynamical objects. So remember, this includes both compact and non-compact cycles, and we model that by the compact cycle. Now there is a subtlety. We have to realize that this defect group is actually not the group of higher form symmetry, but the higher form symmetry is actually only a subset of this. So I'll explain why this is not. Okay, so when we have a non-compact manifold, we can have torsional cycles at the boundary, and this implies that we cannot fix the boundary conditions. So when we start with a string theory on a non-compact manifold, we should fix the boundary conditions. And here, because we have torsional cycles, we cannot do this. Why? Because okay, so the boundary conditions, we associate these flux operators to them. So we measure them by these flux operators, which measure the torsional part of flux expectation values for the type 2B fields. And these operators, when there is torsion, they do not commute. So we cannot in turn fix the boundary conditions. Now, we are actually interested in geometries for which the boundary only have torsion in H5 in order to get our 4D superior angle series. And this can be written using Kuhn formula as the second cohomology of the four-dimensional space where the filter leaves times the defect group. Okay, now here we want to make an important assumption, and that is the boundary conditions should be in one-to-one correspondence with the elements of the Hilbert space. Now, if the boundary has torsional cycle, we said that the operators phi sigma do not commute, which in turn implied that we cannot fix the boundary conditions. Now, our assumption means that the fact that we cannot fix a boundary condition means that the Hilbert space is going to have a grading and split into a direct sum like this, where each factor is labeled by an element in H5 modeled by the torsional part. So if torsion is 0, then obviously there's no grading. Now, so the boundary conditions are in one correspondence with the elements of the Hilbert space. Then we can define the partition function to be, so we can take an element of the vector space dual, the vector space dual to the Hilbert space, and then for each element of the Hilbert space, we get a complex number giving us a partition function. Now, if we cannot fix the boundary conditions, this means that we are going to have, for each boundary condition, we are going to get a different partition function. So we don't have a partition function, but a set of them. Now, how do we fix this problem? We just want one partition function. So to do this, we can pick a maximal subgroup of L in the defect group such that all this sigma, for all the sigma in that subgroup, the corresponding phi sigma operators commute. And then we can decompose the Hilbert space in terms of the eigenvalues of these commuting operators, and finally fix the boundary conditions by giving vacuum expectation values to these maximally commuting set of operators. Okay, so to see how this works, let's look more explicitly at our example. So we start with type 2B theory. We put it on M4 times X6, where X6 here now takes the explicit form of a 2 torus multiplied by C2 mod and ADE subgroup of SU2. Now by Maclay correspondence, we get a 4D Yang-Mills theory with gauge algebra G gamma. Now, what is a defect group? So here we know C2 is mod gamma is a cone over S3 mod gamma. So our 5-dimensional manifold, the boundary of X6 is just a product of S3 mod gamma times T2. And using Kuhn formula, we can work this out, and we find that it is the 2-factor abilization of gamma. So if we say we take gamma to be Z2, then what we get is 2 factors of Z2 for the defect group. And now, like I said, to fix the boundary conditions and so on, we need to pick a maximal isotropic subgroup here. And here we can either take the first Z2 factor, in which case we get the SU2 group, or take the second factor, in which case we get SO3, or the diagonal subgroup, in which case we get SO3 minus. And this reproduces the result we discussed and was given by Arni Sarvik and Tachiko. In fact, these groups are related by the SL2Z duality and the rotations of the torus. Okay, so here I've given some more examples. So if we take gamma to be of different types, say D type or E type, then each time we find that defect group is 2 factors of this gamma AB. So we can each time find what the global structure of what are the possible global structure for our filter. Okay, now in other papers, we also consider different type of constructions where we can consider type to be on, again, M4 times X6, but this time we take X6 to be a hypersurface in C4, and we can define this by picking, say, so these are GG prime edges Douglas. So we can, for example, pick G to be A and G prime to be D, then we add these polynomials corresponding to their duals dual singularity and add these to get the hypersurface in C4. And then for this example, we find that they have a one-form symmetry given by one-form symmetry with associated group as the H, where H is given by this formula for odd n. Now, we can consider a lot of other examples. For example, we can start from type 2A F theory or M theory. We looked at these examples of obtaining 4D n equal 1 or 7D n equal 1 super Yang mills from M theory, or we could for example, consider putting M theory on Calabi-Yau singularity, so Calabi-Yau toric variety, so that we get a 5-dimensional super conformal field theory, and we find that this theory has 1-form and 2-form symmetries with some defect group depending on the geometry. Okay, so in this talk, we discussed what are high-form symmetries, and we also talked about how they can have theories with the same local structure can have different global structures. We also discussed how we can obtain them from the high-form symmetries. We can obtain them from geometric engineering by reducing dimensionality, and we saw that if you have a non-compact internal space, that would result in higher form symmetries. And we saw that the topology, basically these homology groups of the boundary, gave us the defect group. More explicitly, we look at the example for the super Yang mills, which we obtained from type 2B. Now, there are many future directions one can take. Currently, we are looking at finding the mixed Luft anomalies of these symmetries using anomaly inflow. So say, like we discussed, let's make it ND, so some theory in higher dimension, and we get some, then we put it, say, on a singularity, internal space with a singularity, say C2 mod gamma, multiplied by another manifold where our field theory lives. And then we said that we would like to modify this geometry to get so that every special slice has this form. And then what we can do is integrate out the internal space in such a way that we obtain a theory in D plus 1 dimensions. And this is precisely the anomaly theory, topological quantum field theory for our D-dimensional field theory. Again, one could also go and try to, as another direction, try to find high form symmetries for other type of field theories. And also another thing one can do is look at dual theories, which are defined by the fixed points of RG flow, and see which ones can flow to each other. So we can see which ones are actually dual each other by checking whether they have the same higher form symmetries or not. Okay, so there are many papers I should be citing here, but I apologize that I don't have all of them here because there's so much work going on in this on high form symmetries at the moment. And yeah, so thank you for your attention.
Okay, thank you, Sophie, for the great talk. Are there any questions? So in the case of the adverse Douglas theories, did you did you find agreement with previous examples, and also did you like predict results that were not known previously from other field theoretic analysis or from other constructions?
So this one way we could also find the higher form symmetries for these adjust clusters is to look at so these adjust clusters sometimes can be obtained from quiver Lagrangian theories, which have n equal to supersymmetry, and using n equal to 1 Marici Cycle laws, we can get these Agers-Douglas theories, and we expect these Lagrangian theories to have since are connected by Marici Cycle laws to these Agers-Douglas theories to have the same higher form symmetries. And so we find, from the quiver, we can also find the higher form symmetries, and then we can check whether what we found for these high form symmetries using this setup is consistent, and we find that that is the case. I believe that this result was not found before, so to answer your question. Yeah.
Okay, cool, interesting. Any other questions? Okay, if not, then let's thank Sophie again.